All right, we're finally at the time of the year where we get to start talking about mechanisms and reactions rather than all this other stuff. So let's talk about substitution reactions. Substitution reactions are one of the most common types of reactions in organic chemistry. And I'm just going to draw a generic equation up here. And I'm going to abbreviate leaving group as LG. And I've got a nucleophile that I'm going to abbreviate as NU, and it's going to have a negative charge. And the product of this reaction is going to be a substitution where the nucleophile replaces the leaving group. And your leaving group, when it falls off, will have what charge? Negative. Okay, so it's going to have a lone pair and a negative charge. This is the overall reaction for a substitution. Essentially, all that's going to happen is your nucleophile is going to replace the leaving group, right? Pretty easy. The question is, what arrow pushing is required to get from your starting materials to your products? So let's do a couple options. So option one could be that maybe your leaving group falls off first. So your nucleophile really doesn't do anything in the first step. Your leaving group just falls off on its own. And that will give us a set of intermediates where you have a positive charge on a carbon. You've got leaving group now with a negative charge. And your nucleophile is still hanging out, and it also has a negative charge. Okay, what sort of carbocation is this? Is it primary, secondary, tertiary? Secondary. It's attached to two carbons. So we've got a secondary carbocation. Is that a good carbocation? Is it stable? Is it unstable? Is it kind of in the middle? In the middle, so yeah, it's feasible it could go through this mechanism, right? All right, and then what do you think the last step will be in order to get to our product?
The nucleophile attacking the positive.
Yeah, the nucleophile will attack that positive center. And now when we do this, the nucleophile will have a covalent bond, and our leaving group will still be hanging out with the negative charge, right? So that's mechanism one. I think that's perfectly reasonable. But now what we need to do is we need to draw a reaction coordinate diagram for this. Okay, so reaction coordinate diagrams, if you remember, has delta G, or G on one side, and then the reaction progress over here. And we're going to break this into chunks, right? So over here, I'm just going to label this as our starting materials, or SM. What would this be classified as if it's not our products? Intermediate, right? Why didn't I call this a transition state? Because it exists. What is a transition state? Yeah, where bonds are being made and broken, right? In this case, we're showing the bonds completely broken. Okay, and then over here, I'm going to label this as our products. Okay, so let's fill in this chart. I'm going to actually extend this up a bit. I'm just going to put starting materials at some arbitrary energy level. All right, are the intermediates going to be higher or lower in energy than our starting material?
Higher, they're all charged.
Higher, because we've got more charges, right? So I'm just going to write intermediate up here. We're going to have some sort of activation energy, right? So let's label this activation energy. That's the difference in energy going over that hump. So I'm going to call this EA1. All right. Now that we're at our intermediates, we need to go over to our products. Do you think the products are going to be more or less stable than the intermediates?
More stable.
More stable. And then compared to the starting material, if this reaction is spontaneous, do you think your products are going to be more stable or less stable than your starting material? More stable. So if delta G is truly negative, our products are going to be down here. That means a spontaneous reaction, right? And then we have to think about the hump or the activation energy we have to overcome from our intermediates to our product. Do you think it's going to be a big hump or a little hump? Little hump, why? Yeah, that in our intermediate is really unstable. It wants to react with something really quick to form a more stable product. So we're going to have a little hump here. So I'm going to call this EA2. And then down here, we've got delta G for the reaction. Sorry, did you have a question, Diane?
I was just going to say
Yeah. Okay, so this is our reaction coordinate diagram. All right, so looking at this, what is our rate limiting step? Is it going to be going over EA1 or over EA2?
EA1.
EA1, it's the bigger hump. Yep.
So does it really, wait, does it actually really matter where the products are and like whether it's photo up or photo down?
Yeah, we want to know which intermediate or product or starting material is higher or lower in energy than the other. That tells us a lot. So in this case, we know the intermediates are higher in energy than our starting material because they're charged. So we know we're going uphill in that reaction. Okay, so we said that EA1, sorry, I'm going to scroll down briefly, is the rate determining step. Okay, so let's focus on this first step back up in that reaction. So step one, where we're going from starting material to intermediate, what reagent matters the most? Does the nucleophile really matter? No, it's just spectating that whole time. So now what we need to do is we need to write a rate equation. So rate for this equation is going to be equal to some rate constant. And is it going to be first order or second order? What do you guys think? First order, right? Because it doesn't require two molecules running into each other. It just requires one molecule falling apart, essentially. So the rate in this case is going to be equal to the concentration of our first starting material. And let's make a note. The rate limiting step involves the leaving group falling off. The nucleophile doesn't do anything during the rate limiting step. Does that make sense? So that's one potential option for this reaction. We've kind of theorized what the rate equation would be. How could we experimentally prove that this is the case? Does anybody have an idea?
Change the concentration.
Yeah, change the concentration. So for example, I could confirm that this is a valid theory by changing the nucleophile concentration. If I change the nucleophile concentration and it impacts the rate, that means that this probably isn't the correct mechanism. Does that make sense? It's a really simple way that chemists go about checking mechanisms, is doing these theoretical rate laws and then checking which concentration matters and which one doesn't. Okay, so this was option one. We did a pretty good job of splitting that all apart. Now let's do option two. Okay, with option number two, we're going to do a slightly different mechanism. This time it doesn't involve the leaving group falling off first, but we still need to get to the same products. So if our leaving group isn't falling off first, does anybody have an idea for how we can get straight to our product? The nucleophile attacks, right? Okay, so let's try that. So I'll draw this nucleophile attacking right there. Am I done?
Leaving group falling up.
Leaving group falling off too, right? If I draw this as one step, we'd have a Texas carbon. So we need to show this leaving group falling off in that exact same step. Okay, now when we do this, our nucleophile is attached, and our leaving group's falling off. This is a lot easier, right? So let's again draw our reaction coordinate diagram. We've got Gibbs free energy over here. We've got reaction progress. We know if it's a spontaneous reaction that our starting materials must be higher in energy than our products, meaning it's a negative delta G value, and we must still have some sort of energetic hump that we have to overcome, right? So I'm just going to call this, actually I'm going to keep the colors the same. This was our delta G down here. And then we've got our activation energy right here. Okay, so now looking at this, let's do the same thing and try to predict the rate equation. So we know rate is going to be equal to some rate constant little k, and then what matters? Which, yeah, exactly. Both reagents matter because it relies on a collision between two different molecules. So I'm going to fill in this. I'm going to say, all right, this depends on the rate of this times the rate of our nucleophile. And let's try to describe this. The rate limiting step relies on a nucleophile attacking and shoving off a leaving group. That's the scientific term. All right, so now we have two different theoretical reaction pathways. Yep.
So you know how you say the concentration depends on them bumping into one another?
Yeah.
So in the process of that, leaving that, and the nucleophile attacking to where the leaving group is, they actually bump into one another?
Yeah, so for this reaction, the nucleophile is going to run into that first reagent. When it hits that first reagent, the leaving group will get ejected off the other side. Does that make sense? So let's go back and take a look at this one. Yep.
So where you put this starting material in the product. I just want to see if I'm getting this. It depends on the stability of the starting product, right?
Yes, and we will get into the relative stabilities. Right now we're just coming up with two plausible reaction pathways, right? Okay, so when we look at this first option, is this going to be a first order, second order, or third order? First order, right? So the order of the reaction is the sum of the exponents. So in this case, this is a first order substitution. So let's make a note of that. This is referred to as an SN1, holy cow, reaction. And if we break this apart, S means substitution, N means that nucleophile is doing the substitution, and the 1 means first order. So that makes sense, right? We can call this an SN1 because it's first order. What do you think we're going to call option 2? Second order, right? Because it's second reaction order. So let's do that. So second order reaction is going to be SN2. Again, it's still going to be a substitution with the nucleophile that's now second order. All right, so experimentally, how can we confirm that something's a second order reaction, meaning this one, and not a first order reaction? So it may be double concentrations. All right, if I double the concentration of the leaving group, or sorry, the one with the leaving group, does that tell you that it's definitely second order? No, because if we go back up here, that would also double that rate. Okay, so which one should we probably change to double check? The nucleophile, exactly. So let's write that down. Let's say if you double the concentration of your nucleophile, and I'll keep it still negatively charged, and the rate doubles, then the reaction is SN2. And if you double the concentration of your nucleophile, and the rate is unchanged, it is, Sn1. So this is commonly done in a lab setting because we don't immediately know the reaction pathway until we do these experimental studies. Make sense? A lot of this is kind of theoretical, but we're going to delve into how we can predict it even without doing the experiment. So let's focus first on the Sn1 reaction. The Sn1 reaction was this one up here, the one where we kick off our leaving group first. We go through a carbocation, and then the nucleophile attacks in. So let's talk about that starting material, which is also known as an electrophile. Okay, so Sn1 reaction first, and then we'll do Sn2. Okay, so let's compare these. And I'm going to label this reaction A. I'm going to label this one down here reaction B. Okay, in reaction A, I've got an ethyl group with the leaving group on it. And I've got a nucleophile. Again, our nucleophile has a negative charge, just for this example. And then for reaction B, same thing. I've got a nucleophile with a negative charge, but now I've got a tert-butyl group with a leaving group attached. All right, so let's do the reaction pathway for A. If it's Sn1, what will the first step be? So if it's Sn1, that means the leaving group falls off first, right? So Sn1 means our leaving group falls off first in both cases. So let's draw our intermediates now. And then down here, same thing. All right, and then what's the next step going to be?
Nucleophile.
Nucleophile must be the thing that attacks in. Okay, so I'm going to slide this over, and we can show our products. I'm going to slide it over even more. Sorry, I'm running out of room here. And our leaving group is just kind of hanging out with its negative charge out here. All right, so these are our two theoretical reaction pathways. One's for reaction A and one's for reaction B. We know that they're both Sn1 because both of them go through this carbocation, right, where the leaving group falls off first. All right, which reaction pathway do you think is more likely and why? And then check with your neighbor to see if you agree. All right, give me a thumbs up if you think reaction A is more likely. What about reaction B? All right, more thumbs for that one. Who wants to explain why reaction B is more likely? How about somebody in the back who hasn't talked in a while? Anybody back here? What about, all right, Diana?
Tertiary?
The tertiary one's more likely? Why? More stable carbocation. Okay, so if we look at this one, we could say, you know, this is a tertiary carbocation. Up here, we've got a primary carbocation. Which one's more stable? Tertiary. So we can say this goes through the more stable intermediate. This means that it is more likely to occur. Does that make sense? So it's, again, getting back to that carbocation stability trend that we were talking about before. So let's make a little chart. I know this seems kind of redundant, but I like making charts. So we've got tertiary carbocation is more stable than secondary, which is more stable than primary, which is more stable than a methyl carbocation. So we know that carbocation stability increases as we go over to the left. All right, and this trend should be the same for the likelihood of an Sn1 reaction occurring, right? So we could say increasing probability of Sn1. Does that make sense? So the easiest way to tell if something's going to go through an Sn1 mechanism is whether or not it forms a really stable carbocation. If it can form a really stable carbocation, it's way more likely to do Sn1 than Sn2. Because we know that methyl groups and primary groups don't form stable carbocations. All right, let's take a look at another weird example. What about this carbocation? Is that a primary carbocation? Yeah, I'd say it's still primary the way I have it drawn. But what's special about it? What's that? Has hydrogens, it has resonance, right? So resonance can delocalize that positive charge. So this benzylic carbocation is stable due to resonance. And can do Sn1 even though it is primary. Does that make sense? Again, that gets back to that idea that resonance is more important than hyperconjugation. There's also another one that you might occasionally see both in your textbook and on Sapling. Again, this looks like a primary carbocation. You can make the argument primary carbocations don't like to do Sn1 because they're unstable, but this one also has resonance, right? And these are called allylic carbocations. So these tend to do Sn1 because they are resonance stabilized carbocationic intermediates. Make sense? Let's try to do this. What's that?
Just say that last part again.
So when we're looking at the probability of a reaction occurring, we're looking at the stability of our carbocations. When we look at these, students look at these and they say, well, they're primary. That means they're unstable. But they have resonance, which is actually really, really stabilizing. So these are more likely to do Sn1. Yep.
Same with, what's that word?
Allylic.
Oh,
Yeah, so that's an allyl group, and it's allylic carbocation. All right, so let's do the same sort of thought process with Sn2 reactions. And again, a lot of this gets very abstract and conceptual, so feel free to stop me if this doesn't make sense. All right, Sn2 electrophiles. Let's compare two different reactions. In fact, I'm going to do the same two just to keep things consistent. And that'll also be a big hint. All right, if they're Sn2, what will the first step be?
Nucleophile attack with
Yeah, the nucleophile is going to hit the other reagent and knock off that leaving group. Okay? So it's going to hit, kick off the leaving group. It's going to hit, kick off the leaving group. Make sense? So now we've got our nucleophile covalently attached in both of these. And we've got our leaving group that fell off after it was attacked. All right, so now looking at these, which one is more likely to occur? And actually, I'm going to change this arrow just so It's a little bit more clear. So it's going to attack that carbon and kick off that leaving group. Which one's more likely to occur and why? And then check with your neighbor to see if you agree on the why part.
Wait, what did you ask?
What's going on? Which one's more likely to occur? Reaction A or reaction B? And why? This gets very abstract. Imagine that you are the nucleophile. Put yourself in the nucleophilic shoes. Have to get very zen with the nucleophile. I think a good trend might be it's opposite of the one we saw before, but then that gets back to the why. Why is it opposite? We're not going through a carbocation in this case, so we can't make the claim that there's a difference in carbocation stability. What would cause the other one to go faster, though? Does anybody have an idea? What do you think?
Attacking the less stable one is easier.
Attacking the less stable one is easier? So that's a good idea. If we're looking at the two starting materials on the left, the things with the leaving group attached, they're about the same stability, give or take. We will come back to that later, though. So there are ways that you can destabilize your starting materials and cause reaction to go faster. Do you have another idea?
The bottom one attached first, if you make it a Texas carbon, or you really kick it off.
Yeah, so if we tried to attack, you would form a Texas carbon, but you're actually making the bond with that carbon at the same time you're breaking the bond with your leaving group. So we're avoiding Texas carbons by doing that at the same time. What do you think?
Why does the first one do the backside attack easier, right?
Yeah, so let's imagine you're the nucleophile and you have to run into that carbon. This one up on the top does have one methyl group blocking its path. This one has 3 methyl groups that are basically blocking that nucleophile from running into that back carbon, right? So this one is sterically blocked. That makes it harder for the nucleophile to actually reach that carbon that it needs to reach, right? So in this case, Sn2 reactions are more favorable with less bulky substrates. Another word could be electrophiles. So again, let's make a little chart like we did before, where we had primary, secondary, and tertiary and methyl groups. All right, if we think about it this way, the methyl group is the least bulky. Right? That means that the probability of an Sn2 reaction occurring increases the more you get towards methyl groups or primary groups. And this makes it a lot easier, right? Because if we think about SN1, the trends were reversed, right? It was more likely to do SN1 if it were tertiary, where with SN2, it's more likely to do SN2 if it's a methyl group. Does that make sense? Are there any questions with this before we start talking about new stuff? All right, so there's a little bit more we have to consider with these attacks. So let's talk about the stereochemistry. So what's going on in terms of the stereochemistry if there is a stereocenter? So I'll give you guys a warm-up problem. And we're going to do an SN1 example first. Okay, for this warm-up problem, I want you to name this molecule. This one's a little trickier. So we want to find the longest continuous carbon chain. What's the longest chain? 5. Okay, should I go 1, 2, 3, 4, 5? No, we want the substituents to be minimized. So I'm going to go 1, 2, 3, 4, 5. Okay, so we've got a methyl group coming off of carbon 2, a methyl group coming off of carbon 3. So we've got a dimethyl. What will go first, the iodo or the methyl? Iodo. Okay, so we've got 3 iodo, 2, 3 dimethyl pentane. And what am I missing? Stereochemistry, right? So if we do stereochemistry, highest priority for the stereocenter would be the iodine, followed by what? Carbon 2 or carbon 4? Carbon 2. Carbon 4 would be next, and the methyl group would be last. So would this be R or S? R, okay. So if you only have one stereocenter, you don't need to number it, it's implied. So this would be R, 3-iodo, 2,3-dimethylpentane. It's a good review to remember naming. Okay, so now what we want to do is we want to do the Sn1 mechanism. So what's the first step for Sn1? Leaving group falling off. Okay, so I'll draw that falling off. And I'm going to make up a nucleophile in this case. I'm just going to pick chloride as our nucleophile, but we know in step 1 it doesn't do anything. Okay, so in this one, I now have a carbon with an isopropyl group. This ethyl group is sticking back like that. And I've now got a methyl group kind of sticking forward. I've got our leaving group and our chlorine, or our chloride, hanging around. All right, so that carbon is a carbocation, which means we've got a p orbital sticking up and down. And in fact, I'm going to move this leaving group, sorry. I'm going to move this leaving group down here. And it should be iodine, because it's not a generic example, sorry. So can you guys see how it fell off and then we're forming a carbocation in there? All right, so this would be our intermediate. The iodine fell off that bottom half side. The chlorine's just floating around in space trying to find a position to attack. Which side do you think the chlorine will attack? Do you think it'll attack the top side or bottom side or both? Either, right? It's equal probability. You've got a p orbital lobe sticking up, p orbital lobe sticking down. So in this case, you could have a topside attack, or you could have a bottom. Do you think they're equally as likely? Why not? Well, let's think about the iodine too, right? If the iodine fell off the bottom position, it's still going to be hanging out in that bottom area proximity, which again makes that chlorine attack a little bit difficult because it actually has to work its way around that iodine. And that has to do with this interaction right here. So the bottom attack is a little less likely than the topside attack. But let's draw both products. And then I'll write bottom down here. All right, so for the topside attack, I now have a chlorine coming off the top. The isopropyl group is now going to be sticking down like that. The methyl group's still going to be a wedge, and our ethyl group's still going to be a dash. Okay, and then for the bottom one, we know it can possibly occur, but it's a little less likely. The chlorine will be attached. Isopropyl group will still be a straight line. Methyl group will be a wedge. And then this ethyl group will be pointed back like that. What's the relationship between these two compounds? So how are these two compounds up here related? They have the same molecular formula. They have the same connectivity, but they're non-superimposable mirror images, so how would we classify them? Enantiomers. Okay, so with an Sn1 reaction, you end up with a mixture of enantiomers. The top one, if you look at it compared to the starting material, can you see how the chlorine is attached to a different face? So the leaving group, that iodine, was on the bottom side, but now the chlorine's on the top side. What we refer to this as, oops, excuse me, this would be an example of inversion. The other one where the chlorine's on the same face that the iodine once was, this would be called retention. And we know that they're mirror images of one another, therefore they're a mixture of enantiomers. So let's make a note of this, of kind of what's going on. So Sn2 reactions result in a mixture of stereoisomers with a slight preference towards inversion. Why didn't I say a mixture of enantiomers? Yeah, what if I have another stereocenter elsewhere in the molecule that's untouched, right? Then we would have flipped one of those stereocenters, but not all of them. So we might get a mixture of diastereomers if you have other stereocenters in that molecule. But in either case, you'll always scramble one of those stereocenters, meaning you're going to get a mixture of diastereomers. The question is whether or not they'll be diastereomers or enantiomers. Yep?
Got a spelling mistake. Retention are supposed to be a T instead of an
Oh
S.
my goodness. There we go. Thank you. All right, I think that's where we're going to cut it off today. When we come back tomorrow, we're going to do the same stereochemistry analysis, but for Sn2, and I'm going to try to keep it super conceptual. If any of these concepts don't make sense to you, please don't hesitate to email me or stop by my office. I want to make sure that this stuff is clear.